Thanks, everybody. It's really, really a pleasure to be here. I'm going to talk to you about work that we're doing in the Georgia coastal ecosystems, right here on the coast of Georgia, and I'm going to address specifically the question about sustainability of marshes. So before I get there, let's just take a little step back about why do we care about marshes. There are multiple ecosystem services that marshes provide, and they're outlined here. We think about marshes as habitat for many organisms, particularly juveniles. So we think of marshes as nursery grounds. We certainly know that they provide shoreline protection. They're important in filtering out things, especially things that come from the upland, and preserving water quality. They're actively nutrient cyclers. And then there's a lot of attention being paid to the potential for wetlands to sequester carbon. And here's the star of the show for us. Spartina alterniflora is the foundation species for the southeastern salt marshes, and we'll be talking a lot about Spartina today. So I wanted to orient you to our LTER. We're actually at the mouth. This is the watershed of the Altamaha River. In the estuary is where the water then hits the coast down here. This is our domain, that's Sapelo Island. Everywhere that you see a yellow star, we have a sonde in the water that's continuously collecting information, and we go out and do nutrient cruises in the estuary. And then in the adjoining intertidal areas, we're measuring what's happening in the accompanying marshes. Most of our system is salty enough that the intertidal area is salt marsh, so again, it's dominated by Spartina. But when you go up the Altamaha River estuary, it gets progressively fresher, and so the habitat changes. And so we grade from salt to brackish marsh to fresh marsh here that's dominated by the wild rice, Isaniopsis, and then up into tidal fresh forest where you would have bald cypress and tupelo gum and those kinds of species as well. And the reason I'm pointing out some of this habitat shift is that it matters. And so we've studied multiple things about the gradient here, but as you move upstream, we get changes in some of those ecosystem services that I was talking about. So we see increases in biodiversity as you go upstream. There's increases in plant production. We see increased nutrient cycling here. And then we also see changes in the accretion rate. So how fast the marsh is able to maintain elevation. And so my point is that it matters what kind of habitat we have. Okay, so the main question that I'm addressing is how sea level rise affects marshes, and it's really not just the salt marshes, it's all of those systems. This is the long-term trace from Fort Pulaski, which is by Savannah, Georgia, and you can see the long-term trend. It's about a little more than 3 millimeters per year. The GCE has been in business since 2000. We're at Peach, get that, up here. And so you can see, in fact, the slope has probably increased a little bit more. And one of the things to keep in mind is this long-term slope is 3 millimeters per year. So for the marshes to keep up, they need to be accreting at least that much. So that's the long-term backwards trend. If we think about what's happening or what is predicted for the future, it depends on what sea level rise scenario we're thinking about. And so this is a recent NOAA report, and these are sea level rise scenarios up through the next century by 2100. So if we keep it this 3 millimeters per year, we'll raise about 0.3 meters, but the scenarios go up all the way to 2.5 meters, depending on what you're considering. So when people look at these kinds of scenarios and then do projections for marshes, we get headlines like this. This is from the last couple years and sites all around the country where people are worried and concerned that as these increased rates of sea level, what's that going to mean for the marshes? Okay, so let's look at what we've seen at the GCE. Let's start by looking at Spartina. Again, these are all the plots where we have Spartina. My colleague Steve Pennings has run a long-term monitoring program, and this is just the interannual variability in biomass, and there's a lot of factors that contribute to that. But if we're focusing on sea level, I've put that in bold over here on the right. At most of our sites, we see a correlation between sea level and plant production, and what I need to point out is it's a positive correlation. Okay, so increased sea level is causing an increase in Spartina biomass. All right? Just hold that for a second. We've also done Landsat remote sensing, very similar to what Kyle described for the kelp. We've done a similar kinds of analysis for Spartina in our domain. And again, there's a lot of different reasons for this interannual variability that you see, but I've bolded sea level. There's sea levels in the mix, and it's correlated. Again, it's positively correlated. So that might be counterintuitive. So what's going on? Okay, so this is data from around the GCO domain where we look at our long-term average in biomass that we record, so this interannual variability, and I've plotted it relative to elevation, relative to mean sea level, and so the way this looks, inundation is going from right to left, so it's a little bit backwards, but if you look at the Georgia marshes right now, we average about 0.6 meters. That's sort of the average elevation of the marsh platform, and so here I've kind of put in a little bit of water coming on that marsh. If we move an increased inundation and we get to this yellow star, so right at mean, what am I trying to say? Right at the peak here, the water comes up more, it's there for longer, and the plants are actually responding positively, but you can keep going. When we get to mean sea level, we're at the red star, we're actually starting to turn the corner here. And so what's happening in the data that I showed you before is we're sort of between this blue star and the yellow. So that's why we're seeing the increase in productivity, but again, it could kind of turn that corner. So this is just the plants, it's not the whole story. There's feedbacks and lots of feedbacks between the plants and sediment level. And so what we really want to think about is the accretion, so how the marsh elevation varies, and how the ability of the marsh to keep up with that sea level or increasing sediment rate varies with elevation. So this is a similar curve. Again, biomass mostly controls this, and so it looks similar to the biomass curve. But again, where we are here, before I show you where we are, this is something called SLAMM, the Sea Level Affects Marshes Model that we've really tuned for the Altamaha River Estuary, so we've put in a lot of our data, and this is a 1 meter sea level rise scenario. So over the next century, if we get a 1 meter, so we sort of increase sea level, this predicts that the marsh elevation will go from where I told you we were starting at about 0.6, we'll lose about 0.7 meters of elevation. And so, again, we're starting here at that blue star, and then we think about where we're going to go. So for the Georgia marshes, which actually have a lot of sediment coming into them, by 2100, we're still kind of poised right here, so we're sort of okay, but we're at this tipping point where it looks like any more water, and we're going to go under. So when we look at the results of the SLAMM model on a map, here's where we're starting. This is the Altamaha River Estuary, the Salt Marshes, the blue, and then we go up again through brackish and fresh, so up that gradient. By the year 2100, if we have a meter of sea level, the SLAMM model predicts an increase in the marsh area, and then everything kind of shifting upstream where those habitats are. But if we go further, and we think about a 2 meter sea level rise, then you start to drown things towards the mouth. So everything moves even further upstream, but we see an overall decrease in the marsh area and some drowning. So in some ways, the fate of the Georgia marshes depends on how fast that sea level rises. Okay, so I've tried to put this conceptually into this little cartoon here. Well, you'll see how I'm going to build it, but we start with thinking, I've been talking a lot about vertical accretion, and we're thinking about whether the marsh in the vertical direction can keep up with the sea level rise rate. But there's other ways that the marsh can shift and either gain or lose area, and one of them is it can move, again, laterally. Laterally. And this is something that Evelyn was talking about as well. So we're thinking about the salt marsh moving basically upstream as sea level increases and the salt water intrudes further up into what is now the freshwater or brackish parts of the estuary. And so if we take a look at our data again, this is one of our sites, that's our freshwater site, and this is the long-term salinity record. And the red is the monthly maximum salinity that we've seen at that site. And we've had a series of droughts, and every time there's a drought, we do see increases in salinity in this upstream station. And then in the fall of 2016, this is Hurricane Matthew. Fall of 2017, that's Hurricane Irma. So we actually saw a very large intrusion of that salt water. And so when we think about this, the effect of sea level, it wouldn't be an episodic event, it would just be a continuous increase of the salt water getting further upstream. So we were really interested in what that would mean for our freshwater habitat, and we are in the middle of a long-term experiment that was started in 2014 called SALTEX, which stands for Seawater Addition Long-Term Experiment. This is in a freshwater marsh, so the dominant plant here is the wild rice, Zizaniopsis. We have a lot of large-scale plots, and there are multiple treatments, and really the only treatment I'm going to talk about today is the press treatment, where we have continuously adjusted over 4 years the poor water salinity. So this started out as 0 freshwater site, and our target salinity was between 2 and 5. We delivered a mix of salt and fresh water to these plots 3 times a week for 4 years. So we basically kept the salinity slightly elevated. And so again, I'm only going to focus on what happened in the press plots here. So we lost some plants, some biodiversity. Ludwigia was gone within 2 months. This is sort of in the order in which we lost things. Polygonum lasted about a growing season. The Pontidaria lasted a few growing seasons. There's still a few left. And the Zizaniopsis, which is the dominant species, there's some Zizaniopsis, but it's much reduced. Here's a figure showing you one of the press plots. So you can see the sediment is all really exposed, and we've lost a lot of plants. And on the right, we have sediment elevation tables in each of these plots and treatments, and you can see the press plot lost more than 20 millimeters of sediment. So there was no longer any plants holding that sediment in place. We also saw lots of changes in lots of things, but I'm showing you the poor water here first. And so again, circled in red, we saw increases in poor water nutrients, which we think is because of below ground decomposition of when we lost the plant material. And then we also saw depressions in both ecosystem production and respiration. So basically this was a system-wide response, and we're now actually following the recovery of these plots from this manipulation. Okay, so to get back to our diagram, that's lateral migration, and I want to talk about a couple of other ways you could shift marshes here. So one way is you can have erosion or progradation at the edge, so you can either have the shoreline shift inwards or actually accrete outwards. You can also have what's called upland transgression, where you can have the top part of the marsh could actually migrate up in an upland direction. This is a natural marsh with a forested border, so you can think of if salt water if we have an increase in seawater, in sea level, it will start to sort of migrate up and we'll lose some of those trees. That can happen here, but you might actually have a bulkhead or some kind of development up here, and it might not actually allow that upland transgression. So when that happens, we call it something called coastal squeeze, where you start to reduce the area of your intertidal zone, and we've actually looked at that as well. And so that is one of the concerns when there's just sort of no room for the marsh to go up. And that would actually be true in the lateral way as well. If there's no room for the marsh to go upstream, you would have a problem. And then the last mechanism that I want to point out is we can have changes in the interior of the marsh in the marsh open water ratio. So you can have an increase in creek density, or in fact, what I'm going to show you is you can have ponding, and that is something that we see in marshes in New England, where we've seen an increase in the number of ponds, and that will basically start to deteriorate the marsh. So I mentioned New England. I want to sort of widen our scope right now. So I've been talking about the GCE, but there are 2 other LTER sites on the East Coast that have salt marsh as part of their habitat, Virginia Coast Reserve and Plum Island up in Massachusetts. And so we have a Coastal Seas grant in which we're doing a cross-site comparison, thinking in multiple ways about the marshes in these 3 sites and how they vary. And also there's a social science component about how people value marshes in those systems. I'm not going to go into all of this, but I did want to spend a minute on the historical analysis that we've been doing in each of these 3 sites. So the historical analysis, I have a graduate student who's working with me and with Clark Alexander, and she has been digitizing maps of the 3 sites over between 60 and 70 years, depending on what imagery we could get. And she's looking at 2 things. She's looking at changes in the shoreline itself and also changes in the interior marsh features. So the way she looks at shoreline change is through a program called AMBUR. It's an open source R code program that basically draws transects and looks at the difference between different shorelines over time. And this AMBUR analysis for the Georgia coast, everywhere that it's red is a place where the coast is eroding over this approximately 70-year period. Everywhere that it's blue, it's prograding. But there's basically a lot of redistribution. If you look down here, the transects are every 50 meters. It's half and half. So half of them are eroding and half of them are prograding. So not a big change over time. If we look at the other 2 sites, Virginia is similar to Georgia in the fact that it's about half and half eroding and prograding. But if you look at Plum Island, it's a different story. There's a lot more red than blue on this map. About 3/4 of them are red. So we're basically seeing evidence for shoreline shifting and shoreline loss in Plum Island. So that's the edge. The other thing that she's doing is looking at marsh features. And so here again, we'll start with Georgia. We have the marsh and other things mapped over time. This is actually kind of a boring story. There's little change over time, and that fits with what we have modeled and what we're seeing in the system. That's Georgia. When we look at Virginia, there's actually an increase in the marsh area, and I want to sort of focus in on what is happening to the marshes in Virginia. This is the map showing just the marsh change. I want to focus on 2 things. One is the navy blue. So these are areas that were upland and have now converted to marsh. You can see the upland has decreased. So that's evidence for some of that upland transgression that I was talking about, the marsh kind of going up into what was formerly forest. And then the things that are red are areas where the marshes are actually converting to tidal flats. It's not clear why that's happening, but they're actively looking at that in Virginia. And then the last one is Plum Island. This has a different category on here. This is the ponds again, these turquoise areas. There were no ponds in the other 2 marshes. But what's interesting in Plum Island is, again, we're seeing an overall decrease in marsh area. And if we take a look more closely at what's going on with these ponds, with the marsh, everywhere that's red is an area that over the last 75 years or whatever that is, has changed from marsh to pond. There's also, if you can see, there's some pink at the edges where the shoreline has changed also from marsh to water. And so we're seeing more increase in ponds and a decrease in marsh area. I should say this is not directly related to sea level rise for Plum Island, and it is there's historically always been these ponds that form because of ice scouring and other reasons, but the big increase people think is partially because there's a very low sediment coming into these systems, and so there's not sediment there that's helping to fill those in. Okay. So that was the historical analysis, and then we have folks, there's a whole team of folks, modelers, working to put all the information together to kind of look at that whole landscape that I showed you. So my very last point, I'm running out of time, is I just wanted to talk about the social science work that my colleague Colin Polsky has been running. He and his students ran focus groups last summer in each of the 3 sites where they brought members of the public in and they asked them, what do you think about when you think about marshes? What do you care about? What are you concerned about? And then they had a whole bunch of coding of interviews and things that I don't really understand. But basically this is busy, but I wanted to point out that most people identified with cultural benefits. That's what they cared about in marshes. I've been talking about this top one, coastal protection and flooding. It was mentioned, but not nearly as frequently. That isn't what people necessarily identified first. And then he put together these little sentences, which I really like, that say, for Massachusetts, what people think about are recreational experiences and the aesthetics, and the threat that they're worried about is residential development for their marshes. If you look at the other two sort of sentences in Virginia, there's more of this shore identity and shore-based livelihood that gets identified with different risks and threats. And in Georgia, which was interesting for me, there's a lot of sort of history and childhood experiences that people value, and there are different threats and different potential responses. So this project is ongoing. Okay, so my 3 take-home messages for you. First, sea level rise will affect both plant biomass and vertical accretion. In that parabola, that might shift. It can be parameterized for different places. But it's not just about vertical accretion. There's also other ways to gain and lose marsh, and so I wanted to sort of make that point. And then finally, although there are regional differences, the public identifies primarily with cultural ecosystem services. So I started out with a question about sustainability of salt marshes and whether that's still a realistic goal. And my answer, classic science answer, is it depends, but it does. And it really depends in large part on which of these scenarios we're facing in terms of thinking about sea level rise. And then also it's the potential, whether we make more local decisions about whether there is a place for that upland transgression to happen, whether there's sediment available, and whether there's a place for the lateral migration to happen. So basically it comes down to us, I think, because all of that depends on our decisions. So I just wanted to leave you with a picture of the ferry ride going out to Sapelo Island, which is one of the most beautiful places to work. Thank you.
We have time for questions.
I'll just ask from here. I'm Catherine O'Reilly with Ecological Society. I was interested in the policy or the public perception research, and I know that's not your expertise, but in addition to appreciating this as the cultural aspects, was he trying to get at any misunderstandings of the public about how a marsh system works, or what do they understand or not understand about the fundamentals?
So the culmination of this project is that we have charrettes where we're bringing in the stakeholders, mostly the managers, and sharing what we've learned in each of the 3 states. The Virginia charrette is in 2 weeks, I think, or next week. And so that will be an opportunity to actually bring that back, I think, to the decision makers to say, here's what the people here in your system care about. And there's also an economic valuation that's associated with that. So that's still ongoing.
So David Lagomacino, I'm from NASA Goddard, just down the street. And so I wanted to ask a little bit about the SLAMM modeling, and this goes back to a little bit about what Evelyn said about an acceleration that we've seen in sea level. Mm-hmm. So the SLAMM model, you're kind of projecting out to 2100, but there could be short spurts of accelerated levels within 5 to 10 years. Is that incorporated in the SLAMM, and does that have any sort of resilience or vulnerability related to the marsh?
So that's a great question. The way that the trajectory for sea level rise, which I didn't show in the SLAMM model, does have it accelerating. So you get to 1 meter, but it starts out slower and then goes up. There weren't any sort of, if you're asking for sort of more short terms, that was not in there, although I think it's possible to do that. But the other thing which I kind of glossed over is there's feedbacks in there for accretion and the plants moving, so they're built in, but I think there's probably still room to improve that. Somebody said to me, every time they improve the SLAMM model, it gets better. The prognosis gets better.